One of the earliest periodic tables was developed by Mendeleev, where he arranged the elements by atomic weight. And some of the elements that hadn't been discovered yet, he left blanks for, and he predicted physical and chemical properties. And later, it turned out he was right on many of them. Moseley took that periodic table and he arranged them by atomic number, or number of protons, which is similar to the periodic table we have now. Pupils, I'd like you to grab your periodic table that was provided to you by your teacher, and it might be a good idea to color it in and make a key so that you know when we're talking in class, having discussions, if we talk about the alkali earth metals, you should know where they are. The groups are up and down on the periodic table, and they are numbered 1 through 18. So group number 1, excluding hydrogen, is the alkali metals. Group 2, alkali earth metals. And then the skinny part in the middle, you have the transition metals. Non-metals are over to the right on the periodic table, right of the stair-step lines. You have metalloids, or as that calls it, poor metals, which to me seems like kind of a value judgment. And then we have group 18, the noble gases. Down at the bottom, we won't be asked about these elements very often, but you have the lanthanide and actinide series. Oh, group 17, we will often refer to those as the halogens. You need to know that. Horizontally across the periodic table, we have what are called periods. They are numbered 1 through 7. Some properties of elements on the periodic table. Metals, which is most of the elements in the known universe. Metals are shiny, they conduct electricity, they're ductile, malleable, and they lose electrons when they react. Ductile, in case you didn't know, means it can be stretched into a wire or forced through a hole into a wire. Nonmetals, they are not shiny, they do not conduct electricity, and they are not malleable. They tend to be brittle. They gain electrons when they react. Metalloids are elements along the stair-step line. They have properties of both metals and nonmetals. Okay, still working with your periodic table. I hope you've colored it in and you've made a little key. We need to talk about valence electrons now. So in group 1, which includes hydrogen and then the alkali metals, all of those in that group have 1 valence electron. So write that above the group, 1. Group 2, they have 2 valence electrons. And we're not going to talk about the transition metals right now. We'll get to that more when we get to the bonding unit. So 1, 2, skip a few, and you end up over above boron. Those have 3 valence electrons. So all of those in that group, up and down, have 3 valence electrons. And 3, 4, 5, 6, 7, and then 8 with the noble gases. Those are the number of valence electrons. And just as a review, valence electrons are those electrons in the outermost energy level. Along with that, metals, when they react, tend to lose electrons. So those group 1 metals will lose 1 electron and be left with a 1+ charge. Group 2, 2+. Skip the transition metals for now. For groups 13 and 14, if they're a metal, they would tend to lose electrons. If they're a nonmetal, they would gain electrons. So they could be, like group 14 could be +4 or -4. And then 15, 16, and 17, they would gain electrons, -3, -2, -1. And the noble gases do not gain or lose electrons. They are not very reactive. For the remainder of this unit, we're going to be talking about some periodic table trends, atomic radius, ionization energy, and electronegativity. So I'm going to need you to turn your brain on because we're going to be talking about some things that you didn't cover in middle school. There are 2 factors that affect all of those trends. We're going to start with the factor that affects the trend horizontally across the periodic table, and that is effective nuclear charge. You know that nuclear charge is the number of protons in the nucleus, that's Z. The effective nuclear charge is the positive charge emitted by the nucleus that gets beyond core electrons and actually has an effect on those outermost valence electrons. So we're looking at here in this table elements from period 3, sodium, magnesium, aluminum, silicon as we move left to right in that period. Sodium has 11 protons, magnesium 12, aluminum 13, silicon 14. So as we move left to right, the nuclear charge increases. The number of core electrons for those elements in period 3 is 10, and that is a constant because the number of electrons in the first and second energy level, which are core electrons, is not changing. And for every positive charge, a negative charge will cancel it out. One positive and one negative is neutral. So with sodium, it has 11 protons, so it has 11 positive charges in the nucleus. Those core electrons neutralize, for lack of a better term, 10 of that positive charge. That leaves it an effective nuclear charge of 1. Magnesium has an effective nuclear charge of 2 because it has one more proton in the nucleus. So I think you understand that opposites attract. So valence electrons are more strongly attracted to the nucleus when there's a stronger positive charge. So if you look at radius, this is one of the trends that we have to explain. The radius actually goes down as we move left to right across the periodic table because there's a stronger attraction to the nucleus but on those valence electrons in the outermost energy level. So they're held more closely to the nucleus. And if you look at your periodic table, that may not be intuitive because the mass actually increases as you go from left to right in a period. So mass increasing doesn't mean the atom gets bigger. Okay, up and down on the periodic table, the Zeph is relatively constant. If you look at potassium that is directly underneath sodium, potassium has a nuclear charge of 19, but it has 18 core electrons. So the effective nuclear charge for potassium, and in fact all the metals in group 1, is an effective nuclear charge of 1. So the trends up and down on the periodic table within a group are not determined by Zeph. Zeph is the reason for the trends that we're going to be discussing, horizontal, left and right. Okay, let's talk about atomic radius. Atomic radius is the radius of an atom, and it's defined as half the distance between the nuclei of an atom of the atoms in a chemical compound. The periodic trend, horizontal, as the atomic number increases, atomic radius decreases. So maybe you want to write an arrow on your periodic table. As you go from left to right, the atomic radius decreases, as long as we're talking about within one period. And the reason for that is, as we go from left to right, the number of protons in the nucleus increases, which increases the effective nuclear charge, which is the attractive force for those negatively charged electrons. Okay, the group trend, up and down on your periodic table, vertical, if you will. The group trend for atomic radius is not caused by Zeph, that's relatively constant. The reason for the group trend is every time you have electrons in a higher energy level, they are farther from the nucleus. The farther the valence electrons are from the nucleus, the weaker the attraction to the nucleus. And this is all based on Coulomb's law, and you see a formula there in the lower right-hand corner, and don't be alarmed, you don't have to use that formula in any math equations. We just want you to understand it conceptually. F is the force of attraction. Q1 and Q2, that would be the charges that would attract each other, which would be the positive charges from the protons in the nucleus and the negatively charged electrons, and opposite charges cause a force of attraction. In the denominator there, you have the radius squared. So as we add electrons in a higher energy level, they are farther from the nucleus, so that radius increases. So we'd be dividing by a bigger number, which makes that force of attraction smaller. Don't worry about the K. The K is just a constant that we can mathematically apply to two things that are proportional to make them equal. To sum up our discussion of atomic radius, take a look at the general trend. So as we go from right to left, atomic radius increases, as long as we're talking about within an individual period. Up and down, the atomic radius increases as you go down. Please note that we're talking about a general trend here. There may be a few exceptions as you go through some of those transition metals. What I need you to understand is the general trend and be able to explain both the trend left and right and up and down. Okay, we may ask you to compare the radius of an ion compared to the atom that it was formed from. So lithium. Lithium is a metal. It will lose electrons when it reacts, and we end up with lithium 1+. The electron, in this case, that it loses is its valence electrons. So the valence electrons are farther from the nucleus, so the lithium 1+ ion just now has what were its core electrons, so it is smaller. So cations are smaller than the atom that they were formed from. With nonmetals, they tend to gain electrons. So a nonmetal like fluorine will gain an electron, and there's no change in energy levels. It's that fluorine is adding another electron into the second energy level, and we get F1-, but it is much bigger than the atom that it was formed from. So gaining an electron makes the ion bigger than the atom that it was formed from, and not just a little bit bigger, but a lot bigger. And the reason that it gets a lot bigger is electrons repel each other. So you're forcing another electron into that same space in the electron cloud, and those electrons repel each other and they spread out. Okay, pupils, I'd like you to focus on these ions for me. We have what's called an isoelectronic series, where Al3+, Mg2+, sodium 1+, the fluoride ion 1-, O2-, the oxide ion, all of those have the same number of electrons. They've either gained or lost electrons to get 10 electrons. And we have a representation, not to scale there, of their radius. And oxygen, the O2-, is the largest, while aluminum is the smallest. Why do you suppose that is, pupils? Well, I'll tell you why, pupils. It's because aluminum has more protons in the nucleus. So it has a greater positive charge that's going to attract those electrons, making it smaller. Okay, pupils, the next periodic table trend we're going to talk about is ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. So it takes energy to take an electron away from an atom. The first ionization energy means the energy to remove one electron. So our periodic table trend, if we're in the same period, horizontal across the periodic table, then the ionization energy increases as we go from left to right. The reason the ionization energy increases is the same reason that the radius decreases. And that is because as we move left to right across the periodic table, you increase the number of protons. As we increase the number of protons, we increase the attraction electrons have to the nucleus. As the electrons are more strongly attracted to the nucleus, it takes more energy to remove an electron from that atom. The group trend, up and down, is not caused by effective nuclear charge. The group trend, the ionization energy increases from bottom to the top. So ionization energy decreases as you go down the periodic table. The reason that it decreases is because that valence electron that would be taken away from that atom is farther from the nucleus. As the electron gets farther from the nucleus, its attraction to the nucleus grows weaker. So it doesn't take as much energy to remove an electron from a large atom. Okay, to continue with ionization energy, we can remove more than one electron from the same atom. So if we're removing a first electron from an atom, we'd call that the first ionization energy, or I1. We can remove a second electron, or a third, or a fourth. So there you see some equations and ionization energies for aluminum. The energy to remove the first electron from aluminum is 580 kilojoules per mole of aluminum. And you don't need to know what a mole is right now. But the second electron takes more energy than the first. The third electron takes more energy than the second. And the fourth electron takes way more energy than the third. I would like you to stop and think about why that fourth electron for aluminum would take so much more energy than the third. There's a general increase as we remove more and more electrons, but there's a big jump in energy between the third and the fourth. The reason is that fourth electron in aluminum is a core electron. Those first three were valence electrons. So a core electron is closer to the nucleus, so it's going to take a lot more energy to remove. So our takeaway from this, the more electrons you remove from a neutral atom, the more energy is required. Valence electrons take less energy to remove than core electrons. Okay, here you have a table of first, second, third, fourth, fifth, and sixth ionization energy for 20 different elements. And if you look at it closely, you can look at the ionization energies and figure out how many valence electrons each of those elements has. Let's start with lithium. Lithium, the first ionization energy is 520. The second is 7,300 kilojoules per mole. There's a big jump between the first and the second with lithium because lithium only had one valence electron. Take a look at magnesium. Magnesium has two valence electrons, so the lowest, of course, is the first ionization energy, little jump to the second ionization energy, and then a big jump to the third ionization energy, which is 7,730. Aluminium that we looked at on the previous slide, there isn't a big jump until after the third electron because aluminum has three valence electrons. Our last periodic table trend that we want to talk about today is electronegativity. Electronegativity is the ability for an atom to attract electrons to itself in a chemical bond. So the actual trend on the periodic table is exactly like ionization energy. The electronegativity increases as you go left to right across a period because the effective nuclear charge increases. There's more protons in the nucleus, which makes it gives it a stronger attraction for the electrons from a different atom. And then the vertical trend up and down. As an atom gets bigger, it's attracting electrons from farther away. So the attraction that an atom has, that a really large atom has, is less than a smaller atom. So your trend on the periodic table, maybe you want to draw some arrows. Electronegativity increases as you go up, and it increases left to right, with the exception of the noble gases. The most electronegative element is fluorine, and down in the other corner, the least electronegative element is francium, if you can find any francium, because at any time on Earth there's maybe 2 or 3 grams. The noble gases do not have a strong attraction for the electrons from a different atom. They have complete energy levels, and they don't enter into chemical bonds very much. So electronegativity is a concept that we're not going to talk about too much in this unit, but it's going to become really important when we get to the bonding unit coming soon.